Today we talk about the other great half of energy analysis, something called potential energy. We begin with an important definition. All forces can be divided into two categories, called conservative and non-conservative. The reason for the term is not obvious at the moment, but we define such a force to be conservative if the force does zero work around any closed path. Consider the work done by gravity on a box of mass m as is raised to a height L, h, moved over a distance s, and then returned to a starting point along a linear path that makes an angle theta. So blah, ba-da, like that. The total work done is the sum of the work done during each of the three paths. In each of these, it's easy to compute, since in each case the force is just the weight mg directed downward. So along path 1, lifting it through a height h, we have gravity pulling it down, but the displacement is up, so the angle is 180 degrees. So we have the force times the distance times cosine of 180. We get minus mgh. And then along path 2, we have gravity pulling it down, but the displacement is horizontal, so the angle is 90 degrees. And as always, work is zero if the force is perpendicular to the path. So we have mg times s times cosine of 90 over 0, meaning it doesn't matter how far over we pull it. Gravity can't access the horizontal motion and does no work in that case. We'll see that's really important when we talk about energies as well. The final path is a little trickier because now gravity points down and the path is along this angle, and we would need to have mg times L times cosine of the angle between them, which I can't call theta because I used theta in the problem already. So I have to call it phi. And if we look at this, we have mg L cos theta, cos phi, but cosine of phi is sine of theta because cosine of an angle is sine of its complement, and they're complementary. So I have mg L sine theta. But if we look over here, we can see in our triangle, if L is the hypotenuse, that mg L sine theta is just h. And so we end up finally at the work done by 3 is just mgh. Again, all that matters for gravity is the vertical motion, not the horizontal. Now I just put string them together. Total work is the work done in path 1 plus the work done in path 2 plus the work done in path 3. Minus mgh plus 0 plus mgh. It's 0. And any closed path we had taken would be broken into steps like this. It's got to be either vertical or horizontal or a combination of them. So this result holds for any closed path we take at all. So we can say that gravity is conservative. Gravity is, in fact, the poster child for conservative forces. It's the one we'll fall back to as our example on many things. Of course, not all forces are conservative. For instance, the work done by friction around the closed loop. No matter how we break up the path here, friction is always opposed to the actual displacement, so the work done by the kinetic friction is always negative, and so could never add to 0. In some sense, gravity gives and takes in equal measure, but friction just takes and takes and takes. We'll flesh out what's being given and what's being taken just a little bit later. There's an important corollary. If the work done around any closed path is 0, then the work done between any two given points, not necessarily the same point, does not depend on the path taken from one point to the other. Consider two parts to be 2 points of a round trip. That is to say, if we go from point A to point B via two different paths, say path 1 and then path 2, but we can consider going from B back to A as sort of counterpoint 2. Call that 2 star. Well, we know that the total work 1 plus 2 star is 0 because we said the force was conservative. So work 1 plus work 2 star is 0. But clearly going back along the right path is the opposite to going along the green path. So the work 1 minus work 2 is 0, which implies that work 1 equals work 2. That if we have a conservative force, then it must be that between any two paths, the work is path independent, no matter what point you pick. The work can and often does depend on the particular initial and final points, but not on anything in between. They are what we call state functions, and we call this path independence. All right, objects have energy based on a state of motion, that is its kinetic energy, and a system can have energy based on its configuration, that is the relative positions of the parts that make it up. For historical reasons, this gets the name potential energy. It's not a great energy. It's not a great name. For instance, when you increase the separation of the Earth object from the center of the Earth, you store gravitational potential energy in the Earth object system. this energy is then potentially available to do work on the object or the earth or other things. That's why we call it potential energy. Kinetic energy, if the thing hits something else, that kinetic energy will do work. It will exert a force and probably push the object. But potential energy can't, where it is, do work, but it has the ability to be turned into kinetic energy that could do work. That's why we call it potential. It's not a great. We symbolize potential energy with the letter U, just for historical reasons, and it's measured like working kinetic energy in joules. We end up defining not the potential energy itself, but rather its change between two locations by saying that the potential energy difference between 2 points is minus the work done from going between those 2 points. Since the path is not specified, the potential energy is only well defined for conservative forces. In other words, we need the work to be path independent, so we can just say there is a change. For example, gravitational potential energy would be found as what work does gravity do as an object is raised from location y initial to location y final. Since gravity opposes motion, the work done would be the work from A to B is minus, because of the opposite direction, mg, which is the force, times this distance. And we get minus mg delta y. Therefore, the change in potential energy in going up a distance from point A to point B is minus that work, which is minus mg delta y, or just mg delta y. That kind of makes it logical to define the actual potential energy as mgy, your weight times your vertical coordinate. Since y is a coordinate, we have complete freedom to specify its origin, meaning we can specify where the potential energy is 0. We can always pick the 0 point of the potential energy. Having done it once in a problem, though, we have to stay consistent or we'll get nonsense answers. Shown below are stocks of various blocks. They're given in terms of m. Each has the same height and has center of mass in the center of the block. Consider the 0 point to be the height of the center mass of the lowest block. So this is our y equals 0, and therefore u equals 0. And they want us to rank the potential energy, so let's just find it. For case A, we have, let's actually get our heights here. Call this y equals 1, y equals 2, y equals 3. And so for case A, we have 5 times 0 plus m times a height. I guess I should put a g in here too. Plus 5 times mg times 2h plus m times g times 3h. And we see that to be 1 plus 5 plus 3 is 9. mgh. If we do case B, we have 3m times g times 0h plus 3m times g times 1h plus 3m times g times 2h plus 3m times g times 3h, or 3 plus 6 plus 9, 15. mgh. For C, we have 4mg times 0h plus m times g times 1h plus 3 times mg times 2h plus 4m times g times 3h. And that's going to be 1 plus 6 is 7 plus 12 is 19 mgh. And then likewise, we would have 4 plus 6, so that's 10, plus another 6 is 16. And then here we would have 5 plus 10 plus 3 is 18. Putting all of them in place, we have, it was 9, and then 15, and then 19. So our most is here, and our least is there. Potential energy, unlike kinetic energy, has a different form for each type of force. So for instance, for the spring force, the ideal spring forces would give us the potential energy, which is that the potential energy for spring is 1/2 times the spring constant times the stretch squared. Or, because the compression is just negative, also times the compression squared. This so-called quadratic energy is actually one of the most important in physics, and we'll keep coming back to it. But for the moment, we'll just mention that the spring force has an energy which is 1/2 kx squared. If multiple types of force act, then the total potential energy is just the sum of all the individual ones, which is convenient. And remember that energies are scalars, so they're easy to add. As mentioned, not all forces have works that are path independent. Thus, only some forces have associated potential energies. We can define a conservative force as a force for which a potential energy can be defined. All of these definitions turn out to be equivalent. Use whichever one is most convenient.